All right, so our next speaker is Priya Donti. Priya is a PhD student in computer science and public policy at Carnegie Mellon. She's also co-founder and chair of Climate Change AI, an initiative to catalyze impactful work in climate change and machine learning. Priya's work focuses on machine learning for forecasting, optimization, and control, especially in high renewables and power grids. And she's a recipient of the MIT Tech Review Innovators Under 35 Award. So with that, Priya.
And I need to do that workflow one more time. Sorry about that. I'm using a borrowed computer, so dealing with some accessibility preferences.
All right.
Okay, great. Can everyone hear me, see slides, everything? Perfect. Okay, thanks. So as Brandon really put very nicely in his talk, right? There are many domains in which there are constraints and physics and decision-making processes that are very well characterized by optimization problems. And you might have this notion that then, well, if we have these very nice characterizations of optimization problems, then somehow we should use this in our machine learning workflows in these same domains. So today I want to dive into some specific examples in one specific domain, specifically thinking about when we're thinking about climate change related problems and specifically those in the energy sector. How can we actually utilize the knowledge that we have about optimization problems in these specific domains within machine learning workflows using this toolkit of differentiable optimization that Brandon just really nicely gave an overview of. Can you check the mic? Oh, okay. Sorry, the mic's on now. Okay, sorry about that. So for those who couldn't hear that, basically really quickly, building on the last talk, I want to dive into how optimization, differentiable optimization can actually be a really powerful tool in a very specific domain here, climate and energy domains. So why am I talking about climate change? I first really want to motivate. So climate change is one of the most pressing issues that we as a society are facing today. And we're already feeling its effects, from storms to droughts to fires to flooding. These impacts are being felt globally, and they are disproportionately being felt by the world's most disadvantaged populations, which creates a real imperative to act quickly on this issue. In particular, according to the UN Intergovernmental Panel on Climate Change, we as a society need to hit net zero greenhouse gas emissions by 2050 in order to stave off some of the worst effects of climate change. And this requires a rapid transformation across many different societal sectors, from energy to transportation to industry to agriculture to forestry, many domains that the operations research community will actually recognize as ones in which we tend to work, right? In which there are really interesting, optimization and control style constraints and settings that we need to deal with. So I think this, this motivation of climate and energy is, it's a really important area for our communities to be utilizing our tools towards. And a couple of years ago, coming from not the OR side, but the machine learning side, a group of us wrote a paper called Tackling Climate Change with Machine Learning that tried to talk about how machine learning techniques coming from that side of things could potentially be usefully employed across climate and energy areas for things like, forecasting the amount of solar or wind power we have on power grids, or more efficiently managing heating and cooling in buildings, to even doing things like predicting the carbon content of soil in agricultural contexts. So coming at it from the machine learning perspective, right, there are lots of potential ways in which machine learning can potentially address these issues. But machine learning methods are bad at doing some of the things that operations research methods are good at doing. In particular, right, when we start to think about employing machine learning for climate and energy problems, many of these climate and energy problems involve some notion of physics or hard constraints or decision-making procedures that in some sense pure machine learning methods do a really bad job with, but are exactly the kinds of things that operations research style methods are really good at dealing with. So to instantiate this in a particular area, let's think about electric power systems. And when I talk about electric power systems, I'm talking about the systems through which our electricity is produced. and then transported along lines and electrical equipment before it's eventually consumed by end-use consumers like us. So on these kinds of systems, there are lots of physics, hard constraints, and decision-making procedures that come into play. For example, when you put electricity into the power grid, the way that that power flows along the lines in the power grid is dictated by the underlying physics of the system. There are also lots of hard constraints that we need to think about. Things like, if I have a power generator that's producing a certain amount of power, it can only change how much power it produces over a certain period of time by a certain amount. This is called a ramping constraint. And there are also various kinds of stability constraints we need to think about, making sure that our system stays at or near some kind of equilibrium, some kind of electrical equilibrium, in order to make sure that the system doesn't break entirely. In addition, on top of this, we have a lot of decision-making procedures that come into play. For instance, if we have some uncertain prediction of electricity demand, we might ask, how do we schedule electricity supply in a way that minimizes costs or emissions or what have you, subject to all of these physics and hard constraints I just described. And what's happened recently on electric power grids is that these kinds of physics and hard constraints are dealt with traditionally through optimization and control methods. But as we start to incorporate more renewable energy into power grids to deal with climate change related problems, these existing methods are starting to fail. They don't have the speed, they don't have the scale. There are various kinds of things where just using a pure optimization or control-based workflow is really, struggling with as we try to scale the integration of renewable energy into these systems. And that's prompted some, discussion about, can machine learning methods potentially actually help us with these kinds of challenges? For example, we actually use reinforcement learning methods to adaptively control power generators and inverters and batteries and all of these different kinds of devices on electric power grids in a way that is scalable and much faster. And AI and machine learning methods can provide, very dynamic and data-driven control kinds of methods. But what they're really bad at is enforcing the underlying physics and constraints and decision-making procedures on power grids that are essential to enforce. If you employ a pure reinforcement learning-based algorithm on a power grid that is not thinking about these constraints, you're probably going to break the underlying power grid. And this is what exactly the optimization methods that we've been using on the grid have been good at doing so far. Another example, maybe slightly unexpected example, is one of electricity demand prediction, forecasting style settings. I am muted. Okay, cool. So maybe another setting that we want to think about here is forecasting, where AI and machine learning methods are very often used to do some kind of to make some kind of prediction. But as Theos even alluded to earlier in his talk, right, there are lots of places where your prediction objective might not be well calibrated to your downstream, what you're actually using the prediction for. So for example, if you're using a machine learning method to make predictions of electricity demand, and you're later putting that prediction into an optimization problem that's telling you how to schedule electricity supply, then not all mispredictions are created equal from the perspective of the downstream decision-making process. If we think about an underprediction of electricity demand versus an overprediction of electricity demand, that has very different implications for whether you underschedule or overschedule electricity supply downstream. And those have very different consequences. Underscheduling electricity supply is really bad. You might not be able to recoup the electricity supply you need in order to balance the power grid. It's expensive, the grid might break. If you have too much electricity supply downstream, okay, maybe you have some waste on the system, but it's not quite as bad. So if we are creating these, predictive models that are optimized for accuracy, but don't understand the downstream implications of the different kinds of mistakes that they might make, this is also really challenging. And this is potentially a way in which we have to think about, can we more effectively merge the way we think about machine learning style prediction with the way we think about decision making from an operations research perspective. And you'll actually hear about this not just from me, but from two other speakers today as well. So the question I would sort of frame for a machine learning audience or an AI audience here is, how do we reap the benefits of AI that I've mentioned on this slide, the dynamic data-driven control, the ability to do time series forecasting, all of that, while mitigating some of the limitations in terms of, not being good at enforcing physics or hard constraints or dealing with decision-making procedures. And, we're at CPAIOR. The answer here is, can we actually bring some of the operations research and optimization style techniques we know and love into our machine learning workflows in order to actually get the best of both worlds here? And so this is a framework that I am going to call optimization in the loop AI, which is basically a framework for incorporating knowledge of our physics or hard constraints or decision-making processes into the way we construct, for example, machine learning models through the use of optimization problems. In particular, if we have some kind of constraint or physics that we know can be captured by an optimization problem, we can embed it into the way that we construct our machine learning model or into the objective that our machine learning model learns from, using this toolkit of differentiable optimization that, again, Brandon so nicely described just now. We have ways to basically take all these optimization problems from different domains and embed them into our machine learning workflows. And given that we can do that, there's actually enables a lot of interesting things to happen. And so I want to, in the rest of this talk, actually dive into two examples of sort of interesting things you can do once you can kind of take optimization layers as a primitive that you can take for granted, and basically now start to embed domain knowledge through the use of these optimization layers into our machine learning workflows. So in doing this, I'm going to use this just pictorial representation of a machine learning model where X are the inputs, H is the functional form of our model, theta are the model parameters, and H sub theta of X are the outputs. So the first example I gave earlier of ways in which we're starting to try to use machine learning methods in electric power systems is this control setting, where we're trying to control different components on an electric power grid. And we want to maybe do this in a scalable way using something like reinforcement learning, but where we also want to make sure that these methods actually satisfy various kinds of constraints, for example, stability constraints on our system. So this is a reinforcement style setting where we have maybe as an input to our reinforcement learning model some kind of state of our system. The output of our model is some kind of control action. And what we might hope is that if we can formulate our stability constraints or any other kinds of constraints we want to satisfy using appropriate optimization problems, then we can somehow embed those optimization problems into our reinforcement learning model using this framework of differential optimization in order to create a model that just inherently satisfies these constraints. So that's the hope, and I'll talk more about how this actually works. The other example I gave earlier is prediction. This sort of, we want to predict electricity demand in a way that is cognizant of the downstream implications of making that kind of prediction. So this is the predict then optimize setting, which Brandon alluded to, and Paul Grigas will also talk about later today, as will Brian. So this is a kind of setting where we have some kind of predictive model, where, for example, the input to our model might be historical data. The output is some kind of prediction. And downstream of the prediction is some decision that will be made. For example, I will predict electricity demand, and someone will decide how to schedule electricity supply. And if we can write down the relationship between our prediction and the downstream decision as an optimization problem, one might hope that there is some way to feed back information about the quality of our downstream decision into the process we use to train our predictive model, so that that predictive model can make the appropriate trade-offs and avoid making mistakes that are really bad from the perspective of the downstream decision. So this is the high-level motivation, and in some sense, this is the whole talk, right? But what I want to do in the rest of the time is actually to dive into some details of these two settings. So the first is this robust control setting. So the overview here is that, again, we need well-performing control methods that also guarantee the enforcement of various kinds of hard constraints. And the approach I'm going to talk about here is, how we can construct reinforcement learning methods, and specifically deep reinforcement learning methods that are dynamic. They learn from data, but by embedding an optimization problem in the loop, actually end up guaranteeing enforcement of hard constraints we care about. And I'll talk about this in two settings. The first is asymptotic stability in electric power grid, so controlling a power grid in a way that stabilizes the system for some definition of stability. And I'll also talk about a realistic, building control setting where you're controlling the heating and cooling system in a building, again, in a way that satisfies various constraints. So when we talk about controlling a system, there are actually, two main communities that are thinking about this. The first is the reinforcement learning community, and recently the deep reinforcement learning community, which basically says, let's formulate some kind of machine learning model, maybe a deep neural network, have that machine learning model act on some kind of system, figure out, get some kind of feedback about how well that model is acting on the system, and then update its parameters accordingly in a way that actually enables the model to perform better. It's a very trial and error style process. The pro here is that you get really expressive and well-performing control policies because the neural network, the reinforcement learning method or the deep reinforcement learning method has had the ability to try a bunch of stuff out, see what happens in a bunch of different scenarios, and come up with a very nuanced, nonlinear policy that they can recommend for across different kinds of scenarios. The con here, though, is that these kinds of pure reinforcement learning methods are subject to failures and potentially catastrophic failures. You don't really have guarantees on how they're going to perform. And as a result, you actually see a lot of wins for deep reinforcement learning recently, but these often happen in settings like multiplayer games online, where in some sense, the consequence of a catastrophic failure is not that big. Whereas you employ these same kinds of methods on a power grid, the consequence of a catastrophic failure is, of course, huge. On the other side of this, you have the robust control community. And what this community basically says is that provable stability or provable guarantees are foremost. And so what this community tends to do is say, let's write down the form of the kind of guarantee, for example, the stability guarantee that we're trying to get. Let's actually make some kind of simplifying assumptions on the functional form of our control policy, for example, that it's linear. And with all of those things taken together, let's write down some kind of semi-definite program that we can solve in order to come up with a simple policy and a Lyapunov function or some other function that we can use to actually characterize, to prove that the controller that we outputted is actually going to stabilize the system. So the pro here is that you get provable stability, kind of assuming that the assumptions of your underlying method hold, you are going to provably stabilize your underlying system. The con is, though, in order to sort of get the controller that has those kinds of guarantees, you made some kind of simplifying assumption, for example, that the controller is linear. And when you're controlling a very complex nonlinear system, synthesizing a linear control policy leaves a lot of performance on the table. So the question is, can we somehow merge these two worlds? Can we somehow improve performance in the way that deep reinforcement learning methods do, really try to take a very nonlinear policy and explore a system and so forth? But can we still somehow guarantee the same stability constraints that robust control does? And so we can do this actually using the toolkit of differentiable optimization. And so what we do is we say, let's take a neural network that takes in some information about the state of our underlying system and outputs or proposes some kind of action. We don't actually take this action, though. What we do is we say, well, let's use our domain knowledge from robust control and power systems to formulate a set of actions that we would be okay taking for this particular state, a set of safe actions that are parameterized on our current state. And let's actually project the output of our neural network onto this set of safe actions, and then output finally the action we're going to take. This projection onto a set of safe actions is an optimization layer, and one that we can differentiate through. And what this allows us to do is basically say, to view our sort of deep reinforcement learning model as a neural network composed with a projection onto a set of safe actions, all of which we know how to differentiate through end to end, and basically say, great, let's see how good the output is. Let's get some kind of reward. Let's backpropagate through this whole thing in the same way with a standard deep reinforcement learning model. And the ultimate output here is you get a deep learning-based policy that is very nonlinear, very expressive, but that still has the same provable robustness guarantees as the robust control counterpart that we used to actually formulate this projection onto a set of safe actions. Now, the question you're probably, very naturally asking is, okay, great, you've told us that there's some set of safe actions that we can project onto, but where does this actually come from? And I'm going to go through this really quickly just for those who are interested, but I'm happy to elaborate on it later for those who would like to dive further. And the key insight is that we basically steal a bunch of stuff from robust control. We basically try to find a set of actions that are guaranteed to satisfy what are called Lyapunov stability criteria from robust control at the state that we're currently at, even under, in some sense, worst case conditions. If our dynamics misbehave as much as possible, then what is the set of actions that we can find that will still guarantee we'll go towards stability? So basically what we do is we take from robust control some model of the uncertainty in our underlying system. So we have some dynamics, we have some kind of, way we can write down, in this case, I'm not tall enough for this, so I'll use the cursor. So write down the time evolution of our dynamics as some function of our current state, of our action, and of W, which is some uncontrollable disturbance that we can observe in real time, but we don't know what it is going to be. And this disturbance term can actually depend, arbitrarily on our state, on our action, and so forth. And so even though the system actually looks linear in our state and our action, there's this sort of hidden dependence within W on our state and our action, which means that we can actually use this uncertainty model to capture a broad set of nonlinear dynamics models as well. The reason I'm emphasizing that is I mentioned that one challenge with existing robust control methods is that they often make some kind of linear assumption on the underlying controller. And if you have this mismatch between nonlinear dynamics and a linear controller, that's when you're leaving a lot of performance on the table. So that's why I want to emphasize this uncertainty model can actually capture various kinds of nonlinear dynamics. And the only thing we know about the disturbance term is that it's bounded in size by some function of our state and action. But again, within that bound, it can behave in a very nonlinear manner. We also have some kind of Lyapunov function. So you can think of it, for those who don't know about Lyapunov functions, as some kind of potential function for your system, where basically high values mean that you're farther away from some kind of equilibrium, and values that are closer to zero means you're closer to some kind of equilibrium. And we obtain a Lyapunov function using traditional robust control synthesis methods. We assume that we have a linear controller. We assume that we have some kind of Lyapunov function. We solve for the linear controller and Lyapunov function. We throw away the linear controller and we keep the Lyapunov function. So at a high level, we basically use traditional techniques to get a Lyapunov function that works for our system. And then we also have some kind of criteria called an exponential stability criterion, which basically says, if you can show that you decrease your Lyapunov function by enough at every point in time, then you've shown that you're going to stabilize your system over time. Yes?
So the safety constraints, are they in the W or in the V?
Yeah, so the safety constraint is this sort of exponential stability criteria here. So it's if you're basically saying for any Lyapunov functions, if you have a valid Lyapunov function and you can show that you're decreasing it sufficiently at every point in time, then you're basically showing that your algorithm will provably bring your system to some kind of equilibrium over time. So the last thing is the safety constraint that we're actually trying to enforce. Yeah, good question. Okay, and so what we do is we take all this machinery from robust control and say, imagine we're at a specific state. Let's solve for the set of actions that satisfy this safety criterion, this exponential stability criterion, even in the worst case, where worst case basically means that if our disturbance term is as bad as possible within our allowable model, we should still decrease the Lyapunov function even in that case. And so what you're seeing on the slide is basically that written out. You say, well, this left side of this, our safety criterion is the one that actually depends on W. It's not necessarily very trivial to see, but basically the time derivative of the Lyapunov function, which is the left side, it depends on the time evolution of the dynamics, which depends on W, but basically this left side depends on W, the right side does not. And for our particular system model, you can basically say, okay, we can solve that out, we can do the algebra on that, And this set ends up being a convex set in our action space. And it actually ends up being non-empty as well. And this is by virtue of the process that we actually used to solve for our Lyapunov function in the first place. So for those who are not into control, that may have been completely inscrutable. I really apologize for that. But the high level takeaway here really is that there's some way to write down a convex set that characterizes the safe set of actions that we can take at a given state. And that allows us to basically then embed a projection onto this convex set into our reinforcement learning workflow in a way that basically enforces that the output of our reinforcement learning model will satisfy the stability criteria that we care about. So why do we go through all this trouble, right? Why do all of this? And so I want to show some sort of an illustrative result as to why we go through this. So these are some illustrative results on a synthetic norm-bounded linear differential inclusion system. That's a system of the form that I showed on the previous slide. And we're going to compare a bunch of different methods on the y-axis on their LQR cost, which is a control cost. Lower values here are better, and the y-axis is on a log scale. On the x-axis are the different methods that we're comparing. So the first three methods here are all non-robust methods, both from control and from reinforcement learning, methods that are acting on the underlying system but have no stability guarantees associated with them. The middle method here is a robust control method, an LQR method, one that basically says we're going to solve for a linear controller that provably stabilizes the system. And the last two methods here are our methods, which are this hybrid between the robust LQR method and a reinforcement learning method. In the paper that this is based on, there's actually more examples of additional robust control methods we compare against, but just for simplicity, I'm showing a selected subset here. And we compare these methods in two different cases. The first is an ordinary case, where our methods were all trained on some setting of the underlying dynamics, where the disturbance was generated based on some distribution that was unknown to them. And then those methods are tested in a similar setting. We also look at an adversarial setting where after those methods are trained, we actually compute at every point in time, what is the worst disturbance we could apply to the underlying system that is still within the allowable disturbance model, but that would maximally destabilize each of these methods individually. And what I want to show here is basically that if we compare these methods, in the ordinary case, this hybrid reinforcement learning plus control kind of approach improves pretty significantly performance compared to kind of just a standard robust control method. So having the additional expressivity of the neural network is gaining you something in terms of performance in the ordinary case. Now, you'll notice that some of the non-robust methods in the ordinary case do even better than all of the robust methods, right? By not having this robustness constraint, they're able to sort of do things that are even more expressive in the ordinary case and perform much better. But in the adversarial case, what you end up seeing is that all of the non-robust methods go unstable, whereas all of the robust methods, including the hybrids with reinforcement learning, stay stable. And this is basically the key benefit of this kind of method, that you can basically get better performance in an ordinary setting while still enforcing the same stability criteria as robust control. Now, there's one hidden downside here, which is speed and computational cost. Doing this kind of reinforcement learning style method means that you're embedding an optimization problem into every single pass of your method, and that means that you're solving it, you're differentiating through it every step. And so computational cost is absolutely a downside and one that needs to be addressed. I saw a question in the back. Yes.
Yes, I was raising my hand.
Yeah, go for it.
Ordinary case, probably I just missed it, but are you actually considering some sort of simulation? Like, are you simulating like ordinary cases, or is this some kind of real data set?
So this one is it's a simulation, and basically there's just some neural network that is generating a disturbance as some unknown black box function of the state and the action. Yeah, it's a great question.
Okay.
Yes.
I was curious about like the provable guarantees that you get.
Mm-hmm.
Are they this like what exactly do you mean by that?
Yeah, so the question was about the provable guarantees that we get. And the provable guarantee is basically that the underlying method will exponentially stabilize, or the control policy that we get will exponentially stabilize the underlying system. And it's basically because at every step through our projection, we're ensuring that we're decreasing the Lyapunov function by a certain amount, which is sort of the condition that you need to satisfy in order to show exponential stability, basically. Yeah. Great question. Yes.
Yeah, to the cases, you have two kinds of cases here. So the question is, where the realistic cases, whether like in between or more close to the ordinary, or where they are?
Yeah, that's a great question. So the question was basically, are realistic cases closer to ordinary? Are they closer to adversarial, and so forth? It depends on the setting, as is always the case. But one big problem that one faces in, for example, electricity systems is that you have a limited amount of data on which you're training, and you might face distribution shift in the sense that your physics underlying don't change. You still know what the boundaries of your physics are, but your data might shift out from underneath you. And that might not be strictly adversarial, but it might hit some kind of corner of your control policy that you didn't expect that causes it to blow up. So even though I wouldn't necessarily say the answer is that things are closer to adversarial, I think this is a proxy to say, if you have some kind of distribution shift within your assumptions, that you still would stay stable, and that distribution shift is probably the norm rather than kind of being in the same setting that you actually trained on. Yeah, that's a good question. All right, so I really briefly want to just emphasize that even though I talked about this one particular example of, asymptotic stability, this general idea of having a reinforcement learning algorithm that is a neural network followed by a projection onto a set of safe actions is much more widely applicable. So for example, we employed the same kind of technique in a setting where we were controlling the heating and cooling system in a building, where the goal was to minimize energy use while still respecting the constraints of the underlying equipment and maintaining the thermal comfort of the building. And the setting there was fairly similar, right? You have a neural network followed by a projection onto a set of feasible actions and a projection you can differentiate through. And the details basically change in terms of, there is a lot of domain knowledge associated with actually just figuring out the set of feasible actions that you're projecting onto. And again, this is basically a case for, it really makes sense for the kind of reinforcement learning community to work very closely with the operations research community to basically come up with these hybrid methods that make sense in the different settings that we're thinking about. I'm not going to go into the results there because they're a little less important and we're running short on time. But to wrap up this part of the talk, the idea is that we need well-performing control methods that also guarantee enforcement of hard constraints. And the basic insight is that you can take a neural network, project its output onto a set of safe actions that we obtain using domain knowledge. And since we can do this in a differentiable way using optimization layers, this basically can improve the performance of our overall end-to-end method. And there's a lot of additional work to be done here. So the kind of argument of this part of the talk is in some sense that the reinforcement learning community and the robust control community should be talking to each other more deeply, for example, via the use of optimization tools. But this is by no means the sort of definitive paradigm for bridging reinforcement learning and robust control. There's a lot of open space here. And this need to improve computational costs is also huge, because as we start to embed these kinds of optimization problems more routinely into machine learning workflows, getting the computational cost of doing so down is really important. Okay, so in the last couple of minutes, I want to dive into a different setting. So far I've given an example of one specific setting where we can take known optimization problems in a different area, or sort of modifications of known optimization problems in a particular domain, and embed them into a deep learning workflow in order to get the kind of best of the data and optimization kind of settings. The second setting I motivated earlier on was one of the prediction setting, where we are doing some kind of prediction that is operating within some larger decision-making process, where the output of the prediction is going to be used for some decision. And where we want to make sure that our predictive method is not making mistakes that are particularly bad from the context of the downstream decision maker. So the approach here is the construction of decision-cognizant or task-based models, where we basically are embedding some knowledge of our downstream decision-making process into the loss function of our predictive model. And so I'll talk about both a decision-cognizant electricity demand forecasting setting really quickly, the one that I've been motivating, but I'll also show that, again, this paradigm applies even more broadly. And again, this setting will be kind of even further expanded upon and sort of brought to different settings by both Brian Wilder and Paul Grigas later on today. So I've sort of motivated this decision-cognizant demand forecasting setting maybe ad nauseum at this point, but we're looking at a setting where we have some past information, for example, electricity demand, and we're using that to make some kind of prediction of future electricity demand. The usual thing that a sort of machine learning person doing this kind of problem would do is say, well, I want to have a model that is as good at predicting demand as possible. And that might look something like the problem on the slide, where if we have theta, the parameters of our neural network, parameterizing some kind of functional form for our model H. So H sub theta of X is the output of our model, and Y is the actual electricity demand. We might be basically trying to pick the parameters of our neural network in a way that minimizes some loss or some error between our prediction and the actual demand. What I'm basically arguing, though, is not all errors are created equal. Some kinds of errors that might look similar from an accuracy perspective, an overprediction or an underprediction, have actually very different implications downstream. And so we want to actually think about, when we make a prediction, what decision does that imply? And how good is that downstream decision? And so this would imply maybe kind of some kind of swap out in the loss function that we're using, where now we basically say, if I have a neural network with parameters theta that takes in some input X, it's going to make a prediction. The prediction will lead to some kind of decision. And I'm calling Z star X theta the sort of best decision that can be made on the basis of our prediction. And what we want to basically say is, what is the cost of that downstream decision when it acts on our true system? So if I predict electricity demand, I use that to schedule electricity supply, and I see the actual electricity demand later. How good was my electricity supply schedule? How good was the decision that my prediction implied? Pictorially, that looks something like this, where you have a neural network model. It's taking in some information like past demand, weather, time. It's making some prediction of electricity demand. And what we do is we say, let's put that demand prediction into a power system optimization model. For those who are familiar with the domain, this is economic dispatch, but we could do a broader set of models here. But let's put that electricity demand into a power system optimization model and spit out an electricity generation schedule, evaluate the cost of this. And since this power system optimization model is an optimization layer, in quotes, because you often don't think of layers as being parts of your loss function, but it's an optimization layer. You can then differentiate this whole thing. And the reason you want to do this is that taking this kind of decision cognizant approach can really dramatically improve the outcomes of your overall end-to-end system. So to show this, I want to show two different plots. In this first plot, what we're doing is that we're comparing two different models. The red dashed line is a model that cares about optimizing for root mean squared error, so sort of an accuracy optimizing model. And the green solid line is our sort of decision cognizant model. We're comparing on the y-axis the root mean squared error of both of these models' predictions over 24 hours. And we're making sort of predictions at the beginning of a day for the next 24 hours. And in this plot, what you can see is that the root mean squared error network, the accuracy optimizing network, is actually doing slightly better when it comes to the accuracy of its predictions, which is unsurprising in some sense. A model that's optimizing for accuracy is going to do well on accuracy. But if you actually now evaluate these models differently, if you say, let's look at the decision that was made after these models made their predictions, and what the cost of that decision was, both from an economic perspective and a reliability perspective, that's the y-axis, you see that the kind of outcome flips really dramatically. And in fact, our decision cognizant model improves the cost of the decision, or improves the quality of the downstream decision by almost 40% compared to a simply accuracy optimizing model. And the reason for this is that by allowing our model to do slightly worse in terms of accuracy, to make predictions that maybe are slightly less objectively good demand predictions, we enable that model to basically avoid critical mistakes that, or critical mispredictions at critical times, or the worst, both bad kinds of mispredictions that lead to really bad decision-making procedures downstream. Now, this is one setting that I've given, right? You can do something like predict electricity demand in a way that's cognizant of some kind of downstream decision. But this broader paradigm actually applies again to a wider array of settings. So for example, you can use a similar kind of thinking to say, okay, I have some kind of optimization problem that is really slow to solve. For example, this problem of AC optimal power flow in power grids, where this AC optimal power flow problem takes in some inputs like power demand. It outputs something like a power generation schedule in a way that minimizes costs subject to some physics. And we might want to say, well, can we fit some kind of deep learning based approximator to this underlying optimization problem, such that the deep learning approximator has the same inputs and outputs as our optimization problem? The problem with doing this naively would be, well, okay, you fit a neural network to approximate your optimization problem, and it may just, royally miss satisfying your underlying constraints. And so what we can say is, well, let's embed the constraints of the original optimization problem into our loss function and make sure that the output of our model incentivize the output of our model to actually satisfy these underlying physics. And the physics that are in the physics or the constraints that are in this loss function, you can think of them as an implicit function. You can differentiate through them using the implicit function theorem. So sort of a similar style of thinking as before. And the results here, basically, we actually did this for the AC optimal power flow setting for this power system optimization setting. And we actually find that we're able to come up with high quality solutions that have good objective value and have no constraint violations about 10 times faster than a traditional optimization solver. So the summary of this part of the talk is basically, again, that we have often some kind of predictive method that operates within some larger decision-making process or physical process. And we want to somehow take this into account in the way we actually construct the predictive method in the first place. And the way we can do this is by incorporating knowledge of our downstream decision-making process or our downstream physics into the loss function of our predictive model using differentiable optimization. And some future directions here include, one, incorporating a wider range of decision-making paradigms. Like in Brandon's talk, in this talk, I've really stuck to the setting where you can do, you can characterize your optimization problems as continuous optimization problems. I've only looked at the setting here where you have one decision-making procedure, but in reality, predictions are often used for a multitude of decision-making procedures. So how do you actually incorporate a wider range of decision-making procedures into these styles of workflows? And fundamentally, the argument I've made in this portion of the talk is that there are many settings where we want a task-based model that is really well tailored to a particular decision-making setting, but you lose something in terms of the generalizability of the settings in which that predictive model can be used, right? If I tune my predictive model for a particular decision-making procedure, there's no reason to think that another decision-making procedure that uses that same predictive model would actually benefit from this task-based model. So how do you actually quantify the trade-offs between task agnostic and task-based models, and sort of when you would actually want to use each of these and what kinds of tasks could you actually generalize them to? I think that's a really important sort of aspect of work. So to summarize, today I talked about optimization in the loop AI, which is a framework that basically says, let's take the domain knowledge that we have in various settings that we can characterize as optimization problems and embed it into our deep learning workflows in a way that allows us to capture various kinds of physics and hard constraints that we care about. And I talked about the settings of both, developing reinforcement learning algorithms that enforce hard constraints that come from the robust control side of things, and also the construction of predictive models that are cognizant of the downstream implications of their predictions. So I will, thank you so much for listening, and I welcome any questions, and please reach out if you'd like to discuss further as well. All right.
Okay, so we have about 5 minutes for questions. So if you have one, please raise your hand.
Okay, yes.
So in the last thing on the ICRPF, we're just using some kind of physics loss.
are you guaranteeing you're actually satisfying physics constraints, or if I use an universal model, would I break it?
Yeah, so it is not a guarantee, but there's something just for, narrational simplicity. It's something that I actually have glossed over here, which is that even though I kind of consider this physics so forth as part of the loss function, when we're actually using the ACOPF approximation in practice, we continue to run these physics and things like that. So it's not just that this physics is here during training and then during actual use it disappears. We actually continue to actually run this physical power flow model during inference. And we still don't get a guarantee actually, but it helps, right? I think if it were just in the loss function, I wouldn't expect this to actually work. Yes. I'm gonna go, yes.
Just to follow up on that,
Mhm.
when you're training this, are you solving the ACOPF here, or you're not solving?
No, so when we're training this actually, and that's actually an interesting part of this method. It's not a supervised method in the sense that you don't actually need exemplary ACOPF outputs in order to do this method. You just need structural information about the underlying problem. So you need to know what the constraints are. You need to know what the objective function is, but nowhere does this sort of output that an ACOPF solver would have gotten itself actually appear in this workflow. The one thing that we're solving here when I talk about physics, we're solving the power flow problem, which is basically saying, given some setting of power generation, how does power actually flow throughout the grid? We're not solving the optimal power flow problem here, would be the one where it's how do you actually set the power generation? And that's where the computational cost savings actually come from. When you solve the full optimal power flow problem, it's very expensive to do, but just solving the power flow problem, just solving the physics out is not as expensive. And so that's where the saving is. Yeah. Okay. So I'm gonna go here first.
Thanks. So you've mentioned this perspective of taking the optimization knowledge as a differentiable layer, right?
Mm-hmm.
But you could do something differently, like taking a trained model and integrating it into a solver. I think PAIOR does something like that.
Absolutely.
How would you relate those approaches? Like,
Yeah.
The pre-trained predictive models, then going back to a conventional optimizer.
Yeah, so that's a great question. So the question was basically, there's two perspectives on how you can think about kind of approximating optimization problems using machine learning. One of them is just try to learn a machine learning model that replaces the optimization problem altogether. And the other is, can you somehow embed your machine learning model into an optimization problem, into a traditional optimization workflow in a way that, for example, I don't know, identifies warm start points or identifies redundant constraints or something like that. And to be completely honest, I actually don't have a prior or a sort of a thought as to which of these ends up being better. The motivation for this particular work was that sort of V1, what everybody tried when they were thinking about how to use machine learning to approximate optimization problems is just train a neural network to fit it. And what everybody's observation is, well, it's not good at enforcing the constraints, so this method doesn't work entirely. And the only point I really want to make with this is there are ways to sort of embed constraint enforcement into the pure neural network workflow. So we throw out this line of methods, that shouldn't be the reason. There might be another reason, but that should not be the reason. Yeah. Okay, so I think I had, yeah.
So you talk about why the sort of like optimization is important in the demand prediction problem as like the prediction error is not indicative of the actual cost in the downstream optimization.
Yeah.
But do we understand what are the costs? Because if it's just about over predicting and under predicting, you can sort of like take that into account by having a different loss function.
Yeah, that's a great question. So the question was basically, if you sort of know what the decision relevant trade-offs are, could you just, for example, handcraft a loss function that deals with that? And so in this particular paper, we actually also write down a kind of cost weighted root mean squared error loss function where we basically exactly characterize this under prediction versus over prediction aspect point wise. And it doesn't perform as well. And the reason for this is often when you're handcrafting these loss functions, you are doing some kind of point-wise evaluation. So at this particular point in time for this particular hour, did I overpredict or underpredict? But when you're making a decision over some kind of horizon, you're also looking at complex dependencies across your different predictions. Your prediction earlier might enforce some kind of decision early that then gets you into trouble later. And that's the kind of stuff that I think is really hard to capture within a handcrafted loss function, which sort of embedding optimization really helps you deal with. Yeah.
We're
it's a
gonna
great
take
question.
one more question.
All right. Okay.
Yes. Oh, no, sorry, ACOPS.
Oh, sorry. Yeah.
So, just wondering, you're doing OP or just power flow.
In here. Yeah.
But so the optimal part is instead of taking that basically done by the normal.
That's exactly. Yeah, that's a really good way to put it. Basically, the neural network is taking part of the care of the optimal part of optimal power flow. And we still have the actual traditional way of doing the power flow part of power flow. That's exactly right. Yeah.
Okay, so let's thank the speaker again.
Thanks so much, everyone.